Before you decide what is real, before you trust what your eyes and instincts tell you, pause for a moment and consider this. What if the universe does not behave the way you think it does? What if certainty is not the foundation of reality, but only a comforting illusion created by the human mind? This is not a talk about complicated equations or distant laboratories. This is a journey into the hidden rules that quietly govern everything you touch, see, and believe. At the smallest scales of existence, the universe plays by rules that feel strange, uncomfortable, and almost unbelievable. Yet these rules work with astonishing precision. They predict outcomes where common sense fails, and they reveal connections where separation seems obvious. As you listen, you may feel your intuition resist. That resistance is important. It is the signal that you are approaching the edge of familiar thinking. Quantum mechanics does not ask for blind belief. It asks for courage. The courage to accept uncertainty, to question assumptions, and to follow evidence even when it leads into unfamiliar territory. By the end of this journey, the goal is not to leave you with answers neatly wrapped in certainty. The goal is to change how you think about reality itself. If you stay until the end, you may discover that the strangest thing about the universe is not how it behaves, but how deeply you are connected to it in ways you never expected. The first keynote points to a deeply unsettling idea. Reality is not as solid or definite as it appears. In classical thinking, objects are assumed to have fixed properties regardless of whether anyone is watching. A chair exists in one place, a particle has a clear position, and the world runs like a predictable machine. Quantum mechanics quietly dismantles this assumption. At the quantum level, particles do not possess precise values of position, momentum, or energy until an interaction forces those values to appear. Before observation, they are described not as objects, but as mathematical wave functions representing many possible outcomes at once. This means reality exists in a kind of suspended state, where multiple futures coexist. An electron, for example, is not moving along a single defined path. Instead, it spreads out as a cloud of probabilities. Only when a measurement is made does one outcome become real while all others disappear. This challenges the idea that the universe has a fixed script playing independently of us. Instead, reality seems conditional, emerging through interaction rather than existing fully formed. What makes this idea so strange is that it works. Experiments repeatedly confirm that predictions based on probabilities match reality with astonishing accuracy. The universe does not commit to a single version of events until it must. This does not mean human consciousness magically creates reality, but it does mean that interaction, measurement, and information play a fundamental role in shaping what becomes real. Reality, at its core, is not a static structure, but a dynamic process constantly forming itself through observation and interaction. The second keynote reveals a universe governed not by certainty, but by chance shaped through mathematics. In everyday life, we expect causes to lead to specific effects, and we trust that if we know enough information, we can predict outcomes with confidence. Quantum mechanics overturns this expectation at a fundamental level. Instead of exact predictions, it offers probabilities, stating not what will happen, but what is likely to happen. This is not due to ignorance or faulty instruments. It is an intrinsic feature of nature itself. At the quantum scale, particles behave in ways that can only be described statistically. An atom may decay now or much later, and no amount of additional knowledge can pinpoint the exact moment. A particle passing through a barrier may appear on the other side even when classical physics says it should not. These events are not errors or exceptions. They follow precise probability rules that have been verified repeatedly through experiments. The strange part is that while individual outcomes are unpredictable, large numbers of events produce remarkably consistent patterns. This introduces a new understanding of order. The universe is not random chaos, but structured uncertainty. Probability becomes the language through which nature expresses its rules. Instead of fixed paths, reality offers distributions of possibilities, and from those possibilities, stable patterns emerge. When quantum mechanics is trusted, certainty is replaced by statistical truth, and prediction becomes a matter of likelihood rather than guarantee. This shift forces a rethinking of control, knowledge, and determinism, revealing a cosmos where unpredictability is not a flaw, but a fundamental feature woven into the fabric of existence. The third key note introduces one of the most counterintuitive ideas in quantum mechanics. The act of observation is not passive. In classical physics, measuring something is assumed to simply reveal what already exists. A thermometer shows the temperature, a ruler shows the length, and the object itself remains unchanged. Quantum mechanics breaks this separation. At very small scales, measuring a system inevitably interacts with it, and that interaction alters its state. When a quantum particle is observed, it is forced to choose a definite outcome from many possibilities. Before measurement, its properties exist as probabilities spread across different states. Observation collapses. This spread into a single result. This is not because the observer intends to change anything, but because measurement requires interaction, and interaction at the quantum level is powerful enough to reshape the system itself. The observer and the observed become part of one process rather than two separate entities. This idea challenges the notion of an objective reality that exists independently of all interaction. It suggests that outcomes are not fully determined until they are questioned. Experiments such as interference patterns disappearing when particles are measured demonstrate that simply trying to find out what a particle is doing changes what it does. Reality responds to inquiry. The deeper implication is not that human awareness magically controls nature, but that information, interaction, and physical contact are fundamental. The universe is not a finished picture waiting to be viewed. It is an unfolding process in which observation plays an active role, shaping what becomes real in each moment of interaction. In the fourth keynote explores the unsettling idea that a single particle can exist in multiple states at the same time. In everyday experience, an object must be in one condition or another. A light is either on or off. A coin is either heads or tails. Quantum mechanics rejects this either-or logic at the fundamental level. Instead, it introduces superposition, where a particle simultaneously occupies all possible states until a measurement is made. In this condition, the particle is not switching rapidly between states, nor is it hiding a secret, unknown position. It genuinely exists as a combination of possibilities. An electron can be in multiple locations at once, and an atom can hold different energy levels at the same time. These overlapping states interfere with one another, producing effects that have been experimentally observed and precisely measured. The mathematics describing this behavior has been tested countless times and has never failed in its predictions. What makes this idea so disturbing is that it defies common sense. Human intuition is shaped by large-scale objects that obey classical rules, not by particles that behave like probability waves. Yet superposition is not a theoretical guess. It is the foundation of technologies such as quantum computing, where information is processed through multiple states simultaneously. This concept forces a reconsideration of reality itself. Instead of a single, fixed version of events unfolding step by step, the quantum world allows many potential versions to coexist. Only when interaction occurs does one outcome become real while the others vanish, leaving behind a history that appears definite only after the fact. The fifth keynote points to one of the most shocking discoveries in modern physics: entanglement. When two particles interact in a specific way, they become linked so deeply that they can no longer be described as separate entities. Their properties are shared even when they are later separated by vast distances. Measuring one instantly determines the state of the other, regardless of how far apart they are. This behavior seems to violate common ideas about space, time, and communication. In classical thinking, influence requires a signal that travels through space and takes time to arrive. Entanglement ignores this limitation. Experiments show that the correlation between entangled particles appears immediately without any detectable delay. Nothing is physically traveling between them in the moment of measurement, yet the connection remains intact. This phenomenon has been tested under extreme conditions and consistently confirmed, ruling out simple explanations based on hidden signals or prearranged instructions. What makes entanglement especially strange is that it does not transmit usable information faster than light, so it does not break relativity. Instead, it reveals that the universe is more deeply connected than classical physics ever suggested. The particles do not act as independent objects, but as parts of a single system, even when separated. This challenges the idea that space is the ultimate divider of things. At the quantum level, separation is not absolute. Entanglement suggests that relationships, not individual objects, are fundamental, and that the universe maintains connections that persist beyond distance, redefining what it means for things to be truly apart. The sixth keynote addresses the deep conflict between quantum mechanics and human intuition. Human understanding is shaped by everyday experiences. Where objects behave predictably, cause is led directly to effects, and reality follows clear rules that feel logical and stable. Quantum mechanics violates nearly all of these expectations. Particles behave like waves, outcomes depend on probabilities, and observation alters what is observed. These ideas feel wrong not because they are incorrect, but because the human brain evolved to survive in a world far removed from the quantum scale. Trusting quantum mechanics requires accepting results that contradict common sense while still producing perfectly accurate predictions. The theory does not offer comforting explanations or visual clarity. Instead, it delivers mathematical rules that work with extraordinary precision. Even when physicists struggle to interpret what the equations mean philosophically, the equations themselves never fail experimental tests. This creates an unusual situation where understanding how something works is less important than trusting that it does work. This tension forces a shift in how knowledge is defined. Instead of demanding intuitive explanations, quantum mechanics asks for humility. It suggests that reality is under no obligation to match human expectations. When intuition is set aside, a deeper consistency appears, one based on evidence rather than comfort. By challenging intuition, quantum mechanics expands the boundaries of thought. It teaches that truth is not measured by how reasonable it feels, but by how accurately it describes nature. Accepting this lesson reshapes the way reality, certainty, and understanding itself are perceived. When all these ideas come together, a single picture begins to emerge. Quantum mechanics reveals a universe that is not fixed, not fully predictable, and not separate from those who observe it. Reality forms through interaction, unfolds through probability, and maintains connections that defy distance and intuition. What appears strange is not the universe itself, but the limits of classical thinking we bring to it. Trusting quantum mechanics means accepting uncertainty as a feature of nature, not a weakness, and recognizing that existence is shaped by relationships, possibilities, and evidence rather than absolute certainty. In doing so, we move from trying to control reality to learning how to understand it on its own terms. Good luck on your journey of exploration and curiosity. May these ideas inspire you to question deeply, think boldly, and remain open to the wonders that lie beyond intuition. Thank you for your time, your attention, and your willingness to engage with the strange and beautiful truths of the universe. Motive of the eye of